Hey everyone, so in the last two videos I went over the combustion of methane under an excess amount of air, and I derived an equation for the enthalpy of a species in terms of temperature. And if you remember, I defined that equation as being equal to the standard heat or standard enthalpy of formation of an ideal gas plus the changes or the integral of the standard heat capacity at constant pressure with respect to temperature. And so in this video, I'm going to evaluate that integral so we can work with it a little easier, and I'm going to find the changing of enthalpy for each species in the combustion reaction, and then I'll go ahead and find the total enthalpy of the whole stream. And so to do so, I've already gone ahead and imported a couple different libraries here, and our module from our class website right here. And that's just going to allow us to work with the properties of different compounds and just make some of these values easier to bring into the equation. So first of all, I'm just going to go ahead and call in these properties of the 5 species involved. So we have carbon dioxide, methane, water, oxygen, and nitrogen. So I'll go ahead and call those in here. Do oxygen first, nitrogen, carbon dioxide, methane, and water. So these are just the species that are involved in our combustion reaction. And now that we've imported their properties, I'm going to go ahead and work with that integral. So the integral here is just the standard heat capacity at constant pressure, and it's with respect to temperature. And we know that the standard heat capacity at constant pressure is right here. It's just A plus B times this term plus D times this term. And so we want to take the integral of y here with respect to temperature. And to do that, obviously A is just going to be A times T, but this second term and this third term are going to be a little bit more difficult to work with. Of course, these A, B, C, D, and E terms are all just, or variables are all just coefficients that are specific to whatever compound you're working with. And so to do this, if we want to evaluate the integral of this term here, this B term, we can just use Wolfram alpha, and I've gone ahead and typed in B times C divided by T divided by the hyperbolic sine of C divided by T, then squared, and taking the integral with respect to temperature. And it's telling us here that it's equal to B times C times the hyperbolic cotangent of C over T, which is also equal to B times C divided by the hyperbolic tangent of C over T. And then this third term here, the D term, is equal to negative D times E times the hyperbolic tangent of E over T. And so now I'm going to just define a function here that will make it a little bit easier to work with that, specifically that integral term in our enthalpy of a species equation. It's a function of temperature. And we're just going to go ahead and put in the integral of this term right here, or this equation here. And so we'll just go ahead and return and this for A, B, C, D, and E, it's all going to be this CpIg term. It's just the ideal gas coefficient for the the standard heat capacity. So it's A times T plus this second term, which is B times C divided by hyperbolic tangent of C over T. So B times C divided by hyperbolic tangent of C over T. And then we need to subtract this second term right here. So minus D times E times the hyperbolic tangent of E over T. So D times E times hyperbolic tangent of E divided by T. And this is actually currently in joules per mole, and we want this to be in kilojoules per mole just to make it a little bit more, to make these numbers a little bit more conceivable, I guess. And so okay, we're just missing a parenthesis. And so if we do this function at whatever temperature we desire and we subtract this function at 298.15 Kelvin, it will be exactly that integral that we've defined earlier for the standard heat capacity. And so we know that the enthalpy of a species I is equal to the enthalpy of formation plus this term at whatever temperature minus 298.15 Kelvin, or minus that function at 298.15 Kelvin. And so we just need to set an arbitrary temperature that we want to evaluate this at. We're just going to say 500 degrees Kelvin. And so this function here is going to be equal to the enthalpy of formation of an ideal gas plus the function evaluated at 500 degrees Kelvin minus that function at 298.15 Kelvin. And so this is our enthalpy of the entire system. So if we want to display that, it will give us the enthalpies of each component within this system. So the enthalpy of the change of enthalpy of all the species in the system. So the change of oxygen here, it's right here. The changing of the enthalpy of nitrogen is here. The changing of carbon dioxide's enthalpy is here, and then methane and water as well. So say we want to find the total enthalpy of the whole system. Well, to do that, we just have to take the number of moles of each component, multiply it by its changing of enthalpy, and add it all together. So to do that, we can make an array, and this array is just going to be the number of moles for each specific component here. And we'll say we want, 2 moles of oxygen, 3 moles of nitrogen, a mole of carbon dioxide, a mole of methane, and maybe 2 moles of water. So these are all of our moles here for each component, and then we need to take, say if we want that total stream of the system, we just need to multiply, say, the changing of the enthalpy of oxygen with its number of moles here, and then do that for each of the respective components here. So we can just do a dot product, and we can say N and H sub I, which is the enthalpy of the changing of the enthalpy of each specific species evaluated at 500 degrees Kelvin. And it'll give us this value here. So it's going to tell us that this is the total enthalpy of the stream. Now, we are actually given a function that will just tell us the enthalpy of a system at whatever temperature. So we can use that to then match with our defined function here. And if they're comparable, or if we receive the same value, we know that our function that we've defined here is accurate. And so that function, that previously defined function that already calculates this for us, is right here. and 500 degrees Kelvin. And as you can see, we get the same value. So we know that our method of finding the enthalpy of the whole system at 500 degrees Kelvin here with this function is pretty accurate. And we also know that our definition of the enthalpy for specific species I at whatever temperature we desire is also an accurate equation.